I've started recording as well. There was some problem with the Zoom software that I had installed. It was not connecting me with the net, not connecting with the Zoom software. मैंने उसको install किया, दोबारा install किया, and then it started working. Uh, uh, I know it's too late, but I'll still talk about few things. One was about this derivative of e power x that I talked about. Some people argue that this expansion of e power x is equal to this is obtained after having developed most of the ideas in differential calculus. So what is the fundamental proof that the derivative of e power x, that is this one, what is a more fundamental proof for that? Just for the sake of basic queries, the basic or fundamental method of getting derivative of e power x is through the first principle. That is, if you remember, first principle, delta x, oh, 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 oh. Limit delta x approaches 0 of fx plus delta x minus fx divided by delta x. So if you use this, so e power x plus delta x minus e power x divided by delta x, and that gives you e power x common. The rest of it is e power delta x minus 1 divided by delta x. Now this part approaches to 1 as delta x goes to 0. So this means we work out with the help of basic fundamental first principle, then e power x comes out to be e power x. And those who are wondering about how this limit is equal to 1, limit, of course, delta x approaches 0, it can be either verified computationally by taking delta x very, very small and find the value of this. So that's it about what I was talking previously. But we have to work out things leading to basic integrals. Can you see this Word file now? I hope you are. So we discussed these last time. These results. except for the last one. And I ask you to do that yourself. Let me continue with the trigonometric functions, integrals. Uh, some of them starting from 7 to 12. They are direct consequences of elementary facts because derivative of cos x is equal to minus sine x. So the antiderivative of sine x should be minus cos x. Derivative of sine is cos, so antiderivative of cos should be sine. Derivative of tangent is secant squares, so on up till here. The derivative of cosecant is minus cosecant into cotangent, so the antiderivative of cosecant into cotangent is minus cosecant. But when we come to these last two integrals, so we need to look into this more closely, because if I talk about tangent, the tangent is sine upon cos. And we see that we have a function in the denominator whose derivative is minus sine x. So instead of considering sine x, we consider minus sine x. To balance out, we multiply it with minus, and then we have function and the derivative. Function in the denominator, derivative in the numerator. Last lecture, we discussed this to produce this kind of result, du upon u, if u is set to be cos x. And that makes it minus ln u, of course, plus c. And since ln u, u is equal to cos x, it can be written as this. An alternate form, which is given here, this is the basic result. But since we have negative outside, so log की property use करते हुए इसको cos x raised to power minus 1 करें. So that becomes log of 1 upon cos. And that produces this result, log of secant. Whenever an integral results into log function, the argument of log is always put in the absolute sign because log is not defined for 0 and negative real numbers. Same is the case with this integral. के integral cot x so कैसे निकालेंगे? तो cos upon sine, and using the similar technique, we get that numerator in this case cot is cos upon sine. So sine नीचे है, नीचे का derivative cos ऊपर है, लिहाजा ln sine. So we can use that directly. So whenever we have this situation, what situation? Denominator is some function and the numerator में उसका derivative मौजूद है. So इसको as a rule इस्तेमाल करते हुए directly whenever we find some situation, you can write down this result. So for cot x, cos upon sine, so sine can need denominator में function है, उसका derivative ऊपर मौजूद है, लिहाजा you can write down directly ln sine without any substitution. Now there are some other basic functions whose antiderivatives are frequently found in problems. But I want you to know that what is sine hyperbolic. Sine hyperbolic x is defined as e power x minus e power minus x divided by 2, whereas cos hyperbolic x is defined as e power x plus e power minus x divided by 2. So when you take the derivative of sine hyperbolic, it becomes cos hyperbolic. When you take the derivative of cos hyperbolic, it becomes sine hyperbolic. Because taking derivative of, for example, cos hyperbolic means derivative of e power x, which remain as it is, plus derivative of e power minus x, which becomes minus of e power minus x, which is this. So derivative of cos hyperbolic is directly sine hyperbolic, and derivative of sine hyperbolic is directly cos hyperbolic. Similarly, their integrals. And note that in comparison to trigonometric functions where derivative of cos is negative sine, that means sign changes, we don't have such a sign change in the derivative of cos hyperbolic. So antiderivative or integral of sine hyperbolic is directly cos hyperbolic, and the integral of cos hyperbolic is sine hyperbolic. Similarly, we can work out the derivative of tangent hyperbolic to be secant hyperbolic square. But for that, you need to know some of the formulas for hyperbolic function. For example, cos hyperbolic square x minus sine hyperbolic square x is equal to 1. Remember that in case of normal trigonometry, cos hyperbolic square plus cos square plus sine square is 1. But in case of hyperbolic, you can verify that taking the square of this, taking the square of this, and subtracting, you get 1. Similarly, taking these two to define tangent hyperbolic is the same as sine upon cos. Cot hyperbolic is cos upon sine. Secant is 1 upon cos hyperbolic. Cosecant hyperbolic square is 1 upon sine hyperbolic square. So there can be further formulas derived, and these you can find in any book. I will share a list of formulas of hyperbolic functions at some later stage. I just want to mention here that derivative of tangent hyperbolic can be proved to be equal to secant hyperbolic square x, whereas derivative of cot hyperbolic is minus cosecant hyperbolic square. Of course, you can verify all these results using elementary definition of hyperbolic function in terms of exponential functions. So tangent hyperbolic, for example, sine upon cos, and sine upon cos means e power x minus e power minus x divided by e power x plus e power minus x. So ये जो डेरिवेटिव निकाला है वो इसके जरिए मालूम किया जा सकता है, और ये comes out to be 1 upon cos hyperbolic square, that means square of this in the denominator. Similarly, derivative of secant trigonometry के अंदर it becomes secant into tangent, but in hyperbolic function secant hyperbolic का derivative comes out to be negative of secant hyperbolic into tangent hyperbolic, and so on. So these hyperbolic function derivatives and antiderivatives are also fundamental to our understanding of whatever we have to do this semester. Now, this next range of problems which are considered here from 21 to 28, they are all derived using substitution techniques or proved using substitution techniques. And we will be studying these substitution techniques in this course at a later stage, not too far away in the future. Very soon, we will be considering how to get or prove all these formulas using substitutions. So I'm switching to something new. And afterwards, we will have at some stage an article in the same chapter that discusses various substitutions for structures of the type a square minus x square. That means this is these structure. Constant square minus x squared में क्या substitution होगी? Constant squared plus x square में क्या substitution होगी? X square minus constant square में क्या substitution होगी? We will discuss that at a later stage where we can prove all these formulas. So now I'm switching to the next thing. Any question about what we discussed up to now? If there are any people around, at least 8 students are around. If you have any question, please come up with your question. Or I switch to next part. After completing my discussion on review of fundamental elementary integrals or basic integrals, you will find exercise 7.1, and that is now your responsibility to practice questions. You based on all these formulas that are mentioned in this first uh, slide for course 7.1, you can solve, and there you can use each of these formulas directly wherever they are applicable. So if you when you solve 7.1 and you find any problem in solving any particular question, you can send me a query on WhatsApp. You can send me, or you can just wait for the next class, because next class I'll start with taking your queries about 7.1. So let us move forward. The second uh, part of this chapter that we have to explore is integration by parts. Now, most of you should be familiar with using integration by parts wherever this technique is required. Uh, and some of you use this formula, one. Some of you use this UV technique. Some of you, uh, uh, I think you never considered this situation where one of the integral is polynomial. One of the function involved in the integral is polynomial, where you get repeated integration. That means integration by parts is applied repeatedly. As far as elementary problems where you get results by a single application of integration by parts, my preference is mostly this formula one, but I know that many students coming from intermediate or coming from A levels, they like this approach more, but there is no difference. But whenever I'll be solving any problem for demonstration of methods, how they are applied, I'll be following this straightforward. Now, this straightforward formula uh, is developed using what? Our objective is to obtain a formula for integral of product of two functions. Now, this can be done if you have some function capital G whose derivative is one of these two functions. I say the derivative of capital G is small g. That means the antiderivative or integral of small g is the capital G function. अगर ऐसा function available है, then we develop a formula for the integral of the product of two functions. So we take, to develop the formula, we take the derivative of the function f in our objective multiplied by the function assumed, that is capital G, whose derivative is to be the second function. When we take the derivative of fx into capital Gx, what we get using u into v technique of derivative, first function as it is, derivative of second function plus derivative of first function plus second function as it is. Now g prime we have taken as small g, so fx into gx comes here. That means capital G prime is replaced by small g. F prime x into small g will be dealt later. And then we rearrange this equation in what form? We take the integral of the right-hand side. If we take the integral of this, that means we are taking the integral of this. So what should be the integral of this term? Derivative removed, the integral of this term is fx gx. And the integral of this right-hand side is written for the time being as simply as it is. So I've missed the integral sign here. Sorry, we haven't integrated here. Now, here on the left-hand side, we have got two terms. One, the product f into g, which is our objective. The other is f prime into capital G. So integral fx gx, the objective, plus integral f prime into gx, which is this, fx into capital G. Now this was our objective. So हम हमने इस objective को left hand side पे रखते हैं. And this term is taken to the right hand side. But on the right hand side, already what we have got is fx into capital Gx. Fx into capital Gx. So capital Gx was nothing but integral small gx. यहाँ dx मैंने मिक्स कर दिया है. And this term bring on brought to the right hand side, and you get negative sign for this. Integral of product of two things. One is the derivative of the first function from the objective. Second, capital G is nothing but the integral of the second function. So here in this term, we have derivative of the first function, integral of the second function multiplied together. Whatever is the result, then we integrate that. So this is the way we develop this formula for integration by parts. Remember that there is some term missing here. I was mentioning that here it should be dx that I missed. As an example, I've considered a very simple problem, x into e power 3x. So first function x, the second function g. No complication in this problem. First function as it is, integral of the second function, and the second function is e power 3x. Then integral of product of two things. First thing is the derivative of the first function, which is x, and the integral of the second function, which is e power 3x. We take the derivative, we take the antiderivative. Integral derivative of x is 1, and integral of e power 3x is e power 3x upon 3. Integral of e power 3x is e power 3x upon 3 used in both the places. Now here it was just the product of two things which is yet to be integrated. Product of the derivative first function and integral of the second function. Once we have done that, we have to integrate this again, and e power 3x into 1 means e power 3x, and e power 3x antiderivative e power 3x upon 3. So this 1 upon 3 becomes 1 upon 9. Now this is a direct and simple application of the formula. Now those who are interested in using this formula, they should be familiar with these things. I'll not waste time in this. And wherever in exercise of the book you find कि आपने ये following problems you have to solve using this technique. I'm not interested. I'm interested only in the use of the fundamental formula, which can be helpful in all situations. I don't prefer this method because many times we get confused in the use of U and V, and problems arise. Now, there is an interesting situation, and I've at the end of this worksheet, or sorry, this lecture sheet, कि हमारे पास किस टाइप की प्रॉब्लम्स आती हैं जब हम इंटीग्रेशन बाय पार्ट इस्तेमाल करते हैं. We have usually three types of problem. One is directly solvable, जो कि अभी हमने example discuss की. That is directly solvable. The second is repeated integration by parts. And the third one is cyclic integration by parts. Repeated integration by parts, and we have a situation of this type. Let me write down, for example, x square e power x dx. If I quickly go through this, x square integral e power x dx minus integral of derivative of x square, which is 2x, integral of e power x is e power x into dx. And now I have x squared e power x minus 2 times integral x e power x. That means the work is not yet complete. I have to apply integration by part again. That is what I mean, repeated integration by part. Now the first function is x. Second function is e power x minus integral of derivative of first function, integral of second function, integrated. So the end is x squared e power x minus 2 times x e power x minus 2 comes out, e power x integral e power x plus c. And finally, we have e power x common throughout in the functional part of the result, x squared minus 2x from here plus 4 plus c. So if we have a second degree polynomial, we have to apply by parts at least 2 times. If you have cubic here, then you have to apply by parts 3 times and so on. So when you have these kind of repeated integrals, we have a tabular method to obtain this result, which is described here. I have shared this page on the LMS resources. I'll make the corrections and I'll discuss this tabular method next time. And then I'll go to cyclic integration problems. Cyclic integration problems are of the type, say, e power 2x into sine 3x dx. And there you start with, say, this named as I. और जब तुम इंटीग्रेशन बाय पार्ट्स लगाते हो तो दो दफ़ा इंटीग्रेशन बाय पार्ट्स करने के बाद ये दोबारा वापस आ जाता है. So these are cyclic type of problems where integration by parts is used, and there are many other. For example, sine raised to power n. That means higher power of sine, higher powers of cos, higher powers of tangent, higher powers of secant, and so on and so forth. So whenever we have cyclic integration problems that we face, we develop sort of formulas that are called reduction formulas. I stop my discussion here today. Sorry for the loss of time and the problems with the internet connection and the Zoom software, which hopefully have been resolved. मैंने reinstall किया है Zoom को, and I was able to. Now, how many of you are still there? 4-5 लोग अभी हैं, and someone said something. So, any query, any question, or I just stop and end the session? No questions, so I'm stopping recording.